Hi, my name is David Villar. I teach pharmacology at a veterinary school in the country of Colombia. And my students are always struggling and wondering where do formularies come up with maintenance and loading doses. This seems to be a head scratcher where they always get bogged down. So in this video, we're going to demonstrate where those maintenance and loading doses come from. And as you may have already guessed, they arise from pharmacokinetic and pharmacodynamic parameters. So with some simple illustrations, we will hopefully make this easier to understand for those of you that need some revision of pharmacology concepts. And to begin with, we'll start by saying that most drug actions require that a therapeutic concentration of the drug is reached at the target site for a certain period of time, whatever that may be. And those concentrations at the target site are going to be at an equilibrium with the plasma drug concentrations. So as you can see in this graph, if we know the therapeutic range in plasma, all we need to do is maintain those concentrations within that range for the necessary time to achieve whatever effect we desire to attain. And in this case, they have administered a single dose of a drug by an extravascular route, and the duration of action will take place as long as the drug is within that therapeutic range. So in this next graph, we see what happens when the same dose is administered at the same interval. In this case, they were giving it every 8 hours and by an intravascular injection. And ideally, we want the fluctuations of the plasma concentrations to fall within the target or therapeutic range. And we are assuming that within that range, the drug will be doing whatever it's supposed to do, and for the purpose that we're giving it in the first place, whether it's treating an infection or helping the heart pump better or what have you. If the drug has a short therapeutic margin, it'll be important to maintain the concentrations between intervals so that they don't exceed levels that may be toxic. And similarly, we may not want them to fall below a minimum effective level in between intervals. So if you notice, when we start giving the maintenance dose, it will take between 4 and 5 half-lives for the drug to reach a steady state of concentration within the range that we're really aiming for. And in situations like severe infections or very painful conditions, you may not take the luxury of waiting that long, meaning that we want therapeutic concentrations right away. And that's when the loading dose comes into play. The loading dose basically refers to the first dose provided that will put concentrations right where they are desired. So with these preliminaries out of the way, let's see how we can calculate both dosages based on pharmacokinetic parameters. Now let's draw the analogy of the body as being two buckets of water connected by a pipe. The syringe in this case is delivering a certain amount in milligrams of a drug, in this case directly into the blood compartment. And because the blood is rapidly flowing through most organs by action of the heart pumping, that drug will leach out of the blood compartment into the extravascular or tissue spaces. And this will usually occur very quickly in the process of what we know as distribution. As I say, usually within minutes of the injection, and eventually it reaches a point of equilibrium between the well-perfused tissues and the blood compartment. And the concentration at the point of equilibrium will be equal to those basically given in milligrams divided by the total volume in which the drug has distributed, which is usually expressed in liters. So here comes the first pharmacokinetic parameter. By measuring the concentration in blood when the equilibrium has taken place, and since we know the dose that was given, we can calculate the volume of distribution for this drug. Now notice that we have skipped the body weight of the animal in the dose parameter. Otherwise, the volume of distribution would be liters per kilogram of body weight. So as you can see, there is also a faucet that will eliminate the drug from the bucket, which is usually carried out by the liver and the kidneys. And the volume of plasma that will be cleaned from the drug in a given time is usually expressed in milliliters of per minute or liters per hour, and that's what we call the clearance of the drug from the body. So if we knew the clearance and the concentration of the drug that needs to be constant in the blood compartment for whatever period of time is necessary, by multiplying both parameters, it would give us the maintenance dose required. So in this analogy, it would be the amount of drug the syringe needs to deliver in milligrams per unit of time, and that would maintain the concentrations steady in spite of being lost out of the faucet. Now, in other words, what is going out through the faucet, we're replacing at the same time with the syringe. So notice again that we have skipped the body weight of the animal in the clearance parameter. Otherwise, we would have a maintenance dose that would be expressed in milligrams per kilogram per hour. Now, a simple way to calculate the clearance of a drug, which is typically not provided in most formularies, is by multiplying the volume of distribution by the elimination constant. And the elimination constant is the fraction of the drug which is eliminated in a given time. And for most drugs which follow a first order kinetics, we can calculate this by dividing 0.693 by the half-life of that particular drug. So if they give you the half-life of the drug and the volume of distribution, then we can say you're set. We can now put everything together in a single equation that will include the body weight of the animal, and you can see that formula here. The maintenance dose would be the dosage in milligrams per kilogram of body weight given at each interval, and that would be equal to the clearance in liters per kilogram per hour times the desired steady state concentrations in plasma. And if the drug was given by any route other than intravascular, we would have to account for the bioavailability of the drug. In other words, how much of that drug is ultimately reaching the blood to be distributed throughout the body. What about the loading dose? As here we have the same graph as we had before to illustrate different ways of doing this depending on the type of information that you have. If we know the volume of distribution and the concentration that you want to achieve immediately, in this case it would be 200 milligrams per liter, then you simply multiply the volume of distribution by that desired concentration, and with that first dose it would already put you at the Cmax or maximum concentration level, and after that first dose you continue with the maintenance dose. Now the problem is that most of the time all we have is the half-life and the maintenance dose, but we don't have any other information. But we still can calculate the loading dose from those two values. So if we look at this graph, by starting with the maintenance dose, it will put you at the 100 milligram per liter mark. And eventually, if you continue giving the same dose at the same interval, it will eventually reach 200 milligrams per liter. So in this case, what we call the accumulation factor from the first dose until it reaches a steady state will be 2. And that would be what you would have to multiply the maintenance dose to calculate the loading dose. Now another way of calculating the accumulation factor is by calculating the fraction that remains in plasma after each time interval, which is what we're going to call arbitrarily as R. In this case, R would be the minimum concentration at the end of the interval, which is 100 divided by the maximum concentration at the beginning of the interval, which is 200. When you do that calculation, we come up with 0.5, which is basically tells you that 50% of the drug concentration in between intervals was lost. So we could also calculate R by applying this other formula that we have here, which multiplies the constant of elimination by the interval, and you take the antinatural logarithm of that value, and that gives you that fraction that remains after each time interval. And finally, if we have the R value, it's basically easy to calculate the accumulation factor. All you have to do is divide by 1 minus R, and as you can see, again, we attain a value of 2 for this particular example. So in summary, the formulas that we can use to calculate the maintenance dose and the loading dose are shown here. Clearance multiplied by the concentrations in plasma, the steady state, will give us the maintenance dose in milligrams per kilogram per hour. And the loading dose can be calculated by dividing that maintenance dose by 1 minus R. As I mentioned earlier, R is the fraction of the concentration that will be left after the end of the time interval has elapsed. So now let's put this in practice with an example. Let's assume that you're presented with a 20 kilogram dog with a probable septicemic shock that could be associated with a parvoviral infection by the presence of bloody diarrhea. The antibiotic that you want to administer works at a therapeutic concentration of 20 milligrams per liter in plasma, and you have ampules of 20 mils with a concentration of 15 milligrams per mil. So for this antibiotic, the pharmacokinetic parameters that the formulary tells you are a half-life of 8 hours and a volume of distribution of 1.5 liters per kilogram. So the two questions that come up is what will be the infusion rate in milligrams per hour? In other words, what will be the maintenance dose for this dog? And what will be the loading dose that we should give as an IV bolus? If we look at this graph, the infusion rate will simply elevate the concentrations slowly until it reaches a steady state. And as I said before, that will take about 4 to 5 half-lives, in this case 32 hours to reach those steady state levels. And therefore we need a loading dose that will put you at the 20 milligram per liter mark from time 0. After you give that loading dose, you continue with the constant rate of infusion or the maintenance dose. Now the solution for the first question is shown here. We first calculate the clearance by multiplying the constant of elimination by the volume of distribution. And once we know the clearance, we multiply by the desired concentrations of 20 milligrams per liter. And we come up with a dosage rate of 2.6 milligrams per kilogram per hour. Now the dosage needs to be multiplied by the body weight of the animal, and that will give us a total dose of 60 milligrams per hour. If we take into account the concentration in the ampules, that dog should be receiving about 1 ampule every 5 hours. Now, with regards to the second question, the loading dose, all we need to do in this scenario is multiply by the desired concentration of 20 milligrams per liter by the volume of distribution, and that will give us 30 milligrams per kilogram. And when that dosage is multiplied by the body weight of the dog, it should receive a total dose of 600 milligrams, which basically corresponds to 2 ampules of 3 milligrams each, given as a bolus. So basically the loading dose will put us right away at the 20 milligram per liter mark, and then we continue with the constant rate of infusion, which is going to maintain the concentrations steady because the amount of the drug which will be going in will basically be similar to the one leaving the body. And obviously if you did not follow that loading dose with the constant rate of infusion and you were using different intervals, in that case you will need to use the other formula that we showed to calculate the loading dose, and that will take into account how much of the drug will be lost in that time interval. So this is the final slide. I hope I have clarified something that is always kind of a nightmare for many of you interested in this topic. And on future videos, we will address how the body manages to eliminate drugs and why they become and why that becomes important in clinical practice. So until next time, take care and bye bye for now.